Hello. So today we're going to talk about hypothesis testing with two samples, specifically in the case when you're testing the difference between means with dependent samples. Okay, so this is section 8.3. We've got one goal, and the goal is to learn how to perform a t-test to test the mean of the difference for a population of paired data. I want to draw your attention here to the fact that we're performing a t-test, and this is not a mistake. We're actually going to be using the same t-test that we used from section 7.3. Okay. So the next few slides, the next 4 slides or so, kind of just give us the setup and explain how we're going to be performing the t-test. So the big idea is that instead of looking at it like we've got 2 samples, we're really going to be investigating one variable, and the variable is the difference between each data pair. Okay, so remember, we're in a situation where we've got paired data. So our samples are dependent. So we've got paired data, and we're looking at D, which is the difference between entries for a data pair. Now our test statistic is going to be D bar, and D bar is the average distance. Okay, so we'll see some examples of how to do this, but you'll have basically like 2 sets of data, and the 2 sets are paired, so then we could look at the difference, right? So we get, this would be D1 would be the difference between the first pair, D2 would be the difference between the second pair, so forth and so on. I believe this is D8, 1, 2, 3, 4, 5, 6, 7, or D7, right? So our test statistic, D bar, is the sum D1 plus D2 plus all the way up to D7 divided by 7. So it's the average of the differences between the paired data entries. Here we have the requirements for performing our test. The requirements, these are the things we need to verify before we complete the test. The samples must be randomly selected. This one is never going away. You always want your samples to be random. The samples have to be paired, so they're dependent. And lastly, both of the populations have to be normally distributed, or the sample sizes need to be at least 30. And so this again allows us to use our central limit theorem to make conclusions about probabilities regarding the sample distributions. So if these conditions are met, then the sampling distribution for D bar is approximated by a t-distribution, okay, with n-1 degrees of freedom, where n is the number of data pairs. So we've got this this graphic here, which is showing us that the sampling distribution of the average of the differences is modeled by a t-distribution with n-1 degrees of freedom. And here we have on this slide just the notation that's being used. So n is the number of pairs of data. Remember from section 8.1, we had and 8.2, we were dealing with n1 and n2, right? So we would keep track of the size of sample 1 and the size of sample 2. Notice that because we're making the assumption that we're dealing with paired data, your sample sizes have to be the same. So there's no need to differentiate between n1 and n2. In this case, n1 is equal to n2, and we just denote it by n. Okay, so D is the difference between entries for a data pair, and mu sub D is the hypothesized mean of the differences of paired data in the population. So the mu here, so the mu part It's telling us that we're working with means or averages. And then we have this little subscript of D, which is saying, hey, look, we're not looking at the average of sample means. We're looking at the average of differences. Okay, differences between paired data in the population. So what this means is that our, well, let's keep on going, but basically this number right here, mu sub D, is going to show up in our null and alternative hypotheses. Okay. So D bar, so this is red, D bar. D bar is the test statistic, and it's the mean of the differences between the paired data. And SD is the standard deviation of the differences. And now notice here, we've got a formula for SD, and both of these formulas are actually equivalent. So we can jump between these two formulas. Why are these equivalent? It essentially boils down to looking at the formula for this D bar. So since this D bar is equal to, the sum of D over N, right? If you replace D bar with the sum of D over N and simplify things, then that's how you, right? So if you take this and you replace the D bar with the sum of D over N, then you end up with the formula on the right. So, you know, things cancel out, you do your algebra, and you can see that both equations are equivalent. And they are both equations for the standard deviation of the differences. Okay. Now we already, this is just a reminder of when we can use the t-test. Samples need to be random, samples need to be dependent, and either the populations are normally distributed or the number of pairs is got to be at least 30. And let's see here. So this is something that's new. So we'll have our standardized test statistic. The formula for the standardized test statistic is here. So it is the difference in the value, right? So it's the value minus the hypothesized mean over the standard error. So this is our traditional formula for any type of t-value or z-value. T-score, z-score, whatever you want to call it. It's your value minus the hypothesized value over the standard error. Okay. Now, so we've got the same, it's pretty much the same setup. First, you have to verify that you can actually perform your test. Then you've got to identify your null and alternative hypotheses and the level of significance. You got to figure out alpha. And then after that, you've got to either, now this 4, 5, 6, and 7 is assuming that you are doing the critical value and the rejection region method. So if you're doing critical value and rejection region method, then you determine your critical value. That's going to be based on, your critical value is going to be based on the degrees of freedom and your alpha, right? Your rejection region is going to be based on whether you are using left-tailed, right-tailed, or two-tailed tests. So the rejection region is going to be based on the type of test you're performing, left-tailed, right-tailed, or two-tailed, along with the critical values. And then lastly, you calculate your standardized test statistic, right? Find your standardized test statistic and see if it's in the rejection region or not. Of course, we can also perform this middle part here using p-values instead of using critical values and rejection regions. Okay, so this is again the same major process that we've been using since chapter 7, the beginning of chapter 7. So I'm not going to go over it in the same amount of detail. Let's jump straight to this example. Okay, so a shoe manufacturer, well, I don't need to read it to you. I'll pause, you can pause and read it. Okay, so here's what we want to do. The first thing we want to do is let's try to verify. Now, what are we going to need to verify? We're going to need to verify that our, let's see here. So we need to verify that the samples are random, the samples are dependent, and population is normally distributed, or n is greater than or equal to 30. So random sample, random samples, paired samples, and then we've got that normally distributed populations, or n is greater than or equal to 30. Okay, so that's the first thing we want to do, is to verify that. And then the second thing we want to do is, so let's see here. Clearly the data is paired because we're in the classic situation of working with before and after, right? So the old height can be considered before, and the new height can be considered after. Okay, so we are working with paired samples. What about random samples? Let's see here. 8 randomly selected athletes. So our samples are random. And then normally distributed populations are n is greater than or equal to 30, assuming the vertical jump heights are normally distributed. So we've got that assumption. Now notice that n is equal to 8. So let me pick a different color here. So because of this 8 here, so n is equal to 8, and it's also showing up here, n is equal to 8. But that's okay because we've got normally distributed populations. That's what we're assuming. Okay. Now the second thing we need to do is we need to set up our determine our null and alternative hypotheses. So we've got to determine the H0 and HA. Now here I would like to caution you because how to set up the null and alternative hypotheses differs. There are different schools of thought around determining your null and alternative hypotheses. So be careful if you are kind of looking at videos online. Be careful because they might be following a different procedure. They might have different rules that govern how they set up their null and alternative hypotheses, right? So some schools of thought say you always set your H0 is that the difference is equal to 0. For us, that's not how we do it. So let's go ahead and go through how we do it. Now, what is first? We need to figure out our claim, and we say our claim verbally, or write the claim verbally. So the claim is that athletes can increase their vertical jump heights using the training shoes. So the claim, so verbally stating the claim is that using, let's go back, I think it is can increase vertical jump heights using the training shoes. Athletes can increase jump heights. So let's put that in here. Athletes can increase jump heights by using fancy shoes. Okay, now let's rewrite the claim in terms of math. Now here, we need to think about what are we using? What are we testing? We are testing a claim about the average difference in jump heights. So if we're saying that the difference in jump heights, what is the difference? Okay, so in other words, the old jump height minus the new jump height, what is the claim? The claim is that the old jump height should be less than the new jump height, right? Because athletes can increase their jump height, so that means that their old jump height is supposed to be less than the new jump height. And if the old jump height is less than the new jump height, that's the same thing as saying that the old minus the new is less than 0. Okay, so for us, the claim is that mu sub d is less than 0. So you see how we did that? Let's go ahead and write this over here. So our claim is going to be that mu sub d is less than 0, and then mu sub d stands for the old height minus new height. Now, when we write the complement, we'll get mu sub d is greater than or equal to 0. And then the last thing we've got to do is figure out which one is the null and which one is the alternative. Okay, so the null is going to be anything with the equal sign, right? Greater than or equal to, or less than or equal to. And then the HA is going to be mu sub d less than 0. Okay, so we figured out our null and alternative hypotheses. Let's go ahead and kind of... Okay. And to be more specific, the claim is the alternative hypothesis. So I'm going to indicate that here. The claim is the alternative hypothesis. Okay. Number 3 is to determine alpha, but alpha should be pretty easy. Alpha is 10%, 0.10. Alpha is equal to 0.10. Okay, so now number 4, for me, what I'm going to do is I'm going to use the calculator. We're going to do the p-value version of things. And remember, hopefully you have watched the video, so watch the TI-84 video, which shows you how to, this is for section 8.3, which shows you how to, use the calculator. So I'm going to enter in, these numbers here are going to go in my L1. These numbers here are going to go in my L2. And then I'm going to create L3, right? So I enter in my data into L1, enter L1 data, enter L2 data. Then I need to store L1 minus L2 into L3. Okay, because now L3 is what I'm actually going to put into my calculator. So now I go to stat, and then go to tests, and then go to t-test. Let's see here. For me, that is stat. Go over to test. For me, it's number 2, t-test. Okay. Now here, for input, I need to make sure that I choose data. Okay, not statistics, because I want to perform a t-test using the data from L3. So my mu naught is the hypothesized difference, so that's going to be 0. Why is it going to be 0? Because that's the numbers, the same number here and here. So I'm going to enter in 0 for my mu naught. For list, I'm going to enter in L3. For frequency, we can keep that at 1. And now I need to tell the calculator what type of test I'm performing, left-tailed, right-tailed, two-tailed. Looking at my alternative hypothesis, I'm performing a left-tailed. So I'm going to have, so it's got mu, and then it's got not equal to mu naught, less than mu naught, and greater than mu naught. And I want less than mu naught. Okay, so let's go there, less than mu naught. Then I go to calculate, hit enter, and aha, so for my output, here's what I got. So I got that mu less than 0, which is just a repeat of my alternative hypothesis. And I got t equals negative 2.33333. Okay, so that t is the same as this standardized test statistic. Okay. The p-value that I got, so my p-value is 0.0261781526. My x-bar is negative 1.75. My SX is 2.121320344. N equals 8. Alright. So, my next step here is to figure out if I'm going to reject H naught or fail to reject H naught. And I look at my p-value. My p-value is about 2.6%. Okay? And comparing my p-value with alpha, p is small compared to alpha. So since my p-value is less than or equal to alpha, I'm going to reject H naught. Alright. And so the next step after rejecting H naught, the next step is to interpret my decision, and I would say at the 10% significance level, there is, so if I rejected H naught and my claim is HA, there's enough evidence to support the claim. Okay, there is enough evidence to support the claim that athletes can increase their vertical jump heights with those fancy shoes. All right. And that is essentially it. So just to verify, what have we done? We already did this where we state the claim verbally. We did this where we state the claim mathematically. Okay. We identified the null and alternative hypotheses, and we chose which one the claim is. Okay, we did that. We specify the level of significance. Now, choose one. Are we conducting a two-samp z-test for a difference of means? A t-test for a difference of means, mu1 minus mu2, sigma unknown. This is what we're doing. Why? Because we did a t-test, right? So whenever you have dependent samples, you're going to be doing a t-test, assuming. Now, what is the distribution used in the test? T-distribution. Okay. Now, list the requirements. We listed the requirements. You need to have random samples, paired samples, and what is it? A normally distributed population, populations, or n is greater than or equal to 30, random samples, said it in the data, said in problem. Paired samples, how do we know it's paired? Because it's before and after. So data is before and after. And then we just highlight normally distributed populations and said it in the problem. Said in the problem. Okay. And now find the standardized test statistic. We found the standardized test statistic. It was t equals negative 2.3333. What is the p-value? We found that 0.02617811526. One or two complete sentences explain what the p-value means for this problem. So the probability of getting a sample difference, a mean sample difference, a mean sample difference as extreme or more extreme than, what was our mean sample difference? It was, I believe, negative, yeah, our mean sample difference is right here, so it's the, I didn't mean to do that. It's this negative 1.75. X bar equals negative 1.75. And now the note, now that's, so X bar is what your calculator uses, is what the TI-84 uses. The textbook uses D bar. Okay. It's the same thing. The D bar is the average difference here. That for the t-test is X bar. So to get something as extreme or more extreme than D bar equals negative 1.75. What is the probability? The probability is 0.026178, so which is about 2.6%, right? Assuming the true difference is 0, right? So if the true difference in the population is 0, how likely is it that we would get a difference of 1.75 meters or centimeters? I don't know, what were the units for the jumping, because they were jumping, right? Inches. So if there truly were no difference in wearing the shoes or not wearing the shoes, and we choose a random sample, what's the likelihood that we would get an average difference of negative 1.75 inches? We've got like a 2.6% likelihood. That's very unlikely, right? Anything less than 5% is unlikely. It's very unlikely. So that's why we rejected the null hypothesis. We rejected the null hypothesis, which and that allowed us to say, hey, the manufacturers do have evidence, statistically speaking, to, conclude that their shoes make a difference. If you want to jump higher, buy those shoes. All right, and if you want to jump higher by an inch and 75, buy those shoes. Okay. Let's see here. So now for our drawing here, what we want to do is we put in our, so down here is the D bar, and we're going to put in our standardized test statistic, which is negative 2.33. And now the key is that this area, because we're doing a left tail test. How do I know we're doing a left tail test? I know that based on the alternative hypothesis. So we're doing a left tail test. So I'm shading the area to the left, And this area is going to be equal to 0.026178. Okay, so that's how we're connecting the p-value to the standardized test statistic. It's the probability that you would get a value, an average difference as extreme or more extreme than what we got. Okay. And then we did this part, make a decision. The reason for the decision, I think our decision was to reject H naught. The reason, because p-value was less than alpha, less than or equal to alpha. Interpret the decision in the context using complete sentences. We did that part over here as well, right at the 10% significance level. So we could actually just kind of copy, and paste. Whoa, that's kind of crazy, huh? Resize. There we go. All right. That's it. Thanks.